So I want to show you a slide because I'm not a power guy. You see, electrical engineering have so many different concentrations. Power, right? So if you learn power electronics, you can find a job in the power plant or any other places has power engineering related stuff. Or microelectronics, designing chips, digital circuit design, or embedded systems, programming computer chips like this. It could be an embedded system level design, writing C program into it, or designing integrated circuit chips like this. Okay, so this one has memories and integrated circuits. So the reason I want to bring this up is because I have used transformers twice or 3 times in my life. Doesn't like other power engineers. But getting to graduate school, you'll see a lot of power engineers are not really dealing with transformers anymore because these are super established technologies. They don't need innovations. Probably just need people to do some maintenance or things like that. If you see advanced research, people are getting research grants in universities or let's say NREL, okay, these kind of places. Like 90% of the people working in power are just doing smart grid. It's just because not really too many things to innovate or to change anymore. So they just have to spend the time on the software to make the grid power management more smart. So it's basically just algorithms and AI and smart grid. Okay, if you choose that power electronics concentration in the future in electrical engineering, then expect some AI stuff and pure software things instead of playing with transformers. There's no way that I can have a 200,000 volts transformer in the lab and let you play with it, right? It's very difficult. So this is one of the examples I've used. So you can see transformers is able to convert a lower voltage to a higher voltage or higher voltage to a lower voltage. So we have a primary side and a secondary side. So the primary side is the input, the secondary is the output usually. And depending on the number of windings of the coil on each side, that determines the voltage ratio of the primary to the secondary. It's very simple stuff. We don't have to get into the design of the transformers. Nobody's gonna do that since there's just so many available on the market you can directly buy, and no one is really designing it in the U.S. I think. So this is special. I think this is the company in Wisconsin. The reason for that, this kind of transformer is special is it's a surface mount transformer. Doesn't like the big bulky transformers you have seen, right? So you are able to connect the voltage to the primary and then get a voltage out from the secondary. So these are using the surface mount soldering those little tiny pins. You can solder on the surface of the board. There's no deep hole, dip like holes. It's called DIP, dip. It's a dip version package. It's like dipping your chicken wing into the sauce, right? It's dipping. So it's like all the chip pins are dip versions, so you can directly insert into the holes of the PCB. For example, like these ones, these caps are dip packages, so you can insert into the holes and solder from the back. But the disadvantage of the dip versions is if you drill a hole on the surface of the PCB and solder to the back, there's no room to solder other more components on the back because there's a hole, through hole from the top to the bottom. That's why people start thinking about putting everything on the surface instead of drilling holes and using the dip versions, right? So they started using SMT. Sometimes you see the SMD, right? Surface mount device like these ones. Okay, so you can see these transformers are surface mount transformers. It's really special. Probably haven't seen before. And I used this one as I think the ratio is probably like 1:50. So I was able to convert 5 volts. Regular digital logic oscillation. Here's the oscillation over here. Yeah, it's a little low voltage oscillator. Will generate a 40 kHz 5 volts oscillation, and that oscillation is being injected into the input of the transformer and being amplified by 50 times. So you can imagine 5 volts times 50 times is giving you about 200 volts. So after 200 volts, you're getting a 200 volts AC signal output over here, and you're using multiple stages of voltage multipliers to amplify. First, I have to regulate it to rectify it to DC voltage, and then amplify it to a higher voltage. So by using these many stages, they're just repeating. It's called voltage multipliers. So I was able to amplify that DC voltage from 200 volts to 3000 volts. And the goal of that is not really high voltage. And the power is low as well, because you can see I'm only powering up the whole thing using a jet header. Is probably just 1 amp, less than 1 amp. To provide that 3000 volts power voltage. So this high voltage, if you have a very thin and sharp tip with a high voltage on it, it is able to ionize the air and creating negative and positive ions, which is able to attach the dust particles in the air and clean up the air. It's really magical. If you see someone is doing an experiment, have a cup, very clear glass cup, right, and then put a cigarette into it, fill it up with the smoke. You can see it's getting milky and unclear. And then you just insert a very little electrode with 3000 volts on it into the clear glass cup, and will clean up the smoke in the cup like in 2 or 3 seconds. It's magical. That's why we are trying to use this kind of technology to clean up the air in the car, so we can sell it to companies like Toyota and Tesla in the future, hopefully. But the company is trying to buy the product from us, and which is called GPS. Is a leading company in this field, making all these ionizer cleaners for the industry. So just showing you one of the examples of using transformer. I'm not really a power guy, but it's one of like 2 or 3 projects I have worked with the transformers. Okay, so you can amplify voltage. You're asking, why not using an op-amp? Spent 2 weeks on op-amp. Why use transformers? It's microelectronics, right? Op-amps are microelectronics, amplifying from like 2 millivolts to 5 volts. But transformers are from like 1 to thousands or 10,000s, 100,000 volts even. It's high voltage stuff. Okay. All right. Okay, now let's dive into the boring stuff. Homework 10, which is due like 12 days from now. Why do we still have to do it? Yeah, don't rush, okay? First, transformers, okay? Thanks for coming today. I was thinking yesterday was exam, today has snow. It's making a perfect case not attending class today. Still made it, cool. Transformers, this is from homework 10. And the first one, it's just a good example. I'm not trying to directly just teaching you homework problems, but it's a very good example. Problem 9.80. I'm just drawing part of it for now, okay? Marked with a dot over here is indicating the direction of the winding. A, B, there's a V1 plus minus V2. All right, if I label the current like this, I1, I2. So the first thing we need to cover today is if, let me see. I'll just write it down here. It's a better description. V1 and V2 are both positive or negative at the dotted terminal. Then use a plus sign. Where? Here. So V1 over N1. So for example, the turns of this coil is N1. Here's N2. So the ratio here is N1 versus N2 from the primary to the secondary. V1 over N1 equals V1 over N2, but for the absolute value here, all right? If you want to remove that absolute value sign here, and you have to follow this convention. If V1 and V2 are both positive and negative at the dotted terminals, for example here, are they both positive or negatives at the dotted terminal? V1, V2, right? Dot. They are both what? Positive at the dotted terminal. Okay? So what's gonna happen? V1 over N1 equals V2 over N2. Plus sign. Okay, if I put a dot here, if I change this dot here to here, in this case, V1 over N1 equals minus V2 over N2. So for voltage, it's still easy to tell, okay? For current, let me give you an example for current. If I1 and I2 are both directed into or out of the dotted terminal, use the minus sign. For current, it's inverse. Use the minus sign. So voltage following this sign convention here. For current, there's a trick here. So if I1 and I2 are both directed into or out of, so into or out of, both into or out of the dotted terminal, use the minus sign, okay? Look at this one. How could you tell if it's getting into or out of? There's just one dot. For either direction, you can tell, hey, this is going into it, but it's also going out of it. How to tell, right? How could you tell? Just one dot, right? Is this getting into the dot or getting out of the dot for this for I1? We consider getting into because this is on the top of the coil. Okay. Okay. You don't want to start with the coil without a dot. You want to start with the one on the other side of the coil. What about this one? It's getting out. Okay. So. And the number of turns here is N1, N2 for the primary and secondary. So in that case, I1, N1, this is given, okay, this is given. I1, N1 equals I2, N2. Instead of ratio for voltages, for currents like this, N1, sorry. So for this case, they are not both getting into or out of the terminal, because one is getting into, one is getting out of. So this becomes what? I1 N1 equals I2 N2, because you don't want to add a minus sign in front of it. Okay? That covers all the cases. So when you are trying to find out the voltage and currents in the homework assignments, you will be able to know where to add a minus sign or plus sign in front of it by looking at the polarity of the voltage and currents. So let's look at one of the examples on the homework, which is 9.80. Okay. Dot A, B, dot, 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 V1, V2, 50 versus 1, 1 versus 25. Okay, so so ZL is given. ZL is 220 plus J120 ohms. Asking for impedance ZAB. It's the first time we have seen this. ZAB. How do we find a ZAB? It's an effective impedance over here. Why? Because these are also load. They are reactive load over here. Because if you remove the source, they won't do anything, right? So eventually the power is getting transferred to the load by the magnetic field over here in between. So it's forming an effective impedance if you look at everything from the input. And that impedance is called ZAB. Okay, so how do we deal with that? It's actually easier than you thought. Okay, because ratios are given, and these equations are given as well. So V1, we know that V1 over N1, look at the polarity here. Are they both positive and negative at the terminal, dotted terminal for V1 and V2? Are they? Yes, they are. So V1 and V2 for this equation, you need a plus sign over here, right? So you can directly write down this. V1 over N1 equals V2 over N2. So V1 equals what? V2 over N2 times N1, right? Times N1. What about currents? If you label the currents flowing in that direction, I1, I2, I1, N1 equals, what's the sign here? So this current is getting into or out of the node or dotted terminal. Into, right? So this is getting into. I2 is getting out of this node. It's getting out of this node. So I1 N1 equals I2 N2. It's a plus sign over here. I1 equals I2 N1 N2. Combines two equations, do a division, so 1 divided by 2. And you are getting V1 over I1 is what? V1 over I1 is V2 N1 N2 over this whole thing here, I2 N1 N2, which is V2 over I2 times N1 N2 square, right? So you can find out the ratio, the impedance ratio here. you do a square of the ratio times the impedance of the secondary stage becomes the impedance of the first stage. Because V1 over I1, if we imagine this is I1 getting into it, V1 is over here. So we just don't look into the whatever the black box is inside the black box is over here. Just treating everything as an entire load. Okay, so V1 over I1 becomes impedance, effective impedance of ZAB, right? Okay. Same for this. V2 over I2 becomes impedance of the whole thing after V2. Okay. So this is impedance after V2 over I2, and that's the impedance over here. So the impedance over here equals this impedance here after V2 times the square of this ratio. Does that make sense? So that's how we derived everything using the equations. We didn't plug in any of the numbers. It's just from the theory. If you have a ratio like this, then the impedance looking into the system from here equals the impedance looking through the system from here times the square of the ratio of the first stage. That's the conclusion here. Make sense? So can you find out this for the second one as well? So this works for the first stage. It's going to be the same thing for the second stage. Okay, and luckily we know the impedance of the very last stage. I'll just directly write down the equation. Okay. So V2 over I2, if there's a I3 and V3, right? That equals V3 over I3 times ZL times 1 over 25 square for this stage. V2 over I2 here equals impedance V3 over I3, impedance here, times the ratio square. And then you plug in. So V1 over I1 equals, plug this in here, right? And you're going to have V3 over I3 times because this N1 versus N2 is 50 over 1 square, and V3 over I3 is given because the ZL is given, which is this guy. So it's going to be ZL times 50 over 25 square. Okay, so this is a really typical transformer problem. Basic and typical, and I believe it's going to be on the final exam in some of a certain format. But fundamentally, you just need to know the number of turns. How do you deal with the number of turns using the sign convention here? Yeah. Based on exam 1, exam 2, I think it's a lot easier than the homework assignments, right? In the exam, so I believe something similar to this will be on the final, because it's just super fundamental, basic. Okay. So that's the first problem in homework 10, and we have a couple of other problems to cover because homework 10 is actually a lot easier, because you can see starting from here is dealing with complex power. I'm going to cover that in a bit. Same question, just changing numbers for like 10 pages. So simple, right? Same stuff. So I'm going to cover that really quick. Complex powers, how do we deal with that? I'll give you several examples, okay? So complex power, the tutorial and homework assignment, whatever the description over there, is a bit confusing. I don't really like it. So I was looking for some resource online and find out a better way to explain everything. And it didn't even have a sign for complex power. So I'll directly just write px over here, the power complex power, okay? And that equals v times I, because these are all complex numbers. So v times I conjugate, keep in mind. So what is conjugate? A plus bj. The conjugate will be A minus bj, right? So it's v times I conjugate, keep in mind. All right, so the tutorial didn't derive it from here and directly throw some of the average power equations to you guys. So it's really confusing. Another thing you need to know for a sine wave, Vm, it's called a magnitude, that's why it's labeled as Vm, okay, Vm. So that's a function, Vm cosine omega t, right? Or sine omega t, sorry, sine omega t. It's omega sine omega t. And then we pick up a value which is smaller than this guy, which is called, Vm over square root of 2. And we define that as we call it VRMS. It's because we are using this value as the equivalent DC power, effective DC voltage in terms of power delivery for some reason. We are not going to derive the equation. I don't know how to derive it, but the thing is we have been using this for so long. That's a convention in power electronics. So whenever you have a VM, a peak power, because the peak voltage is not always existing, right? So it's going up and down always. So we are using this value to represent the equivalent DC voltage in terms of power delivery. It's just a convention. It's called VRMS. So you'll see this a lot. So the same thing like when you are probing the voltage, AC voltage using a multimeter, but you are using the DC channel. Have you done that before? Multimeter? If you connect your multimeter to the outlet over here, it's 110 volts, right? It's 110 volts. But 110 volts is VRMS actually. So the peak voltage is something else. It's a little bit bigger than that. So eventually you probe it, you are seeing a VRMS on the multimeter. You are probing DC voltage. Because the multimeter cannot read AC. It's always changing, right? It's always changing sine wave. But the multimeter is only reading one value, which is the VRMS, which is Vm over square root of 2. Okay? So for here, these are peak voltages. And we can expand it, which is VRMS. Doesn't matter, it's just a value, right? If it tells you, sometimes you can see the homework assignment is using Vm, which is the magnitude, you should know it's the peak voltage, and sometimes it's just using VRMS. It's very simple, it's just the peak magnitude divided by square root of 2, that's it. Nothing fancy here. It's just using the VRMS to define the average power and whatever the reactive power as a definition in our calculations. We just need to use VRMS. It's just a number calculated from V magnitude, right? So this one, VRMS angle, for example, the voltage has a phase shift. Usually it's 0, but let's assume there's a phase shift. It's called theta V. And the I is going to be I RMS theta I, because it's conjugate. So we have to add a minus sign in front of it. Tell me if that makes sense. For example, this complex number, so this one's phasor format is a squared plus b squared, and the angle is what? Arctangent b over a, right? What about the conjugate of this guy? Still the same amplitude, a squared plus b squared, and the angle is what? Minus, because there's a minus sign. So it's going to be minus arctangent b over a. That's why I's conjugate will be IRMS angle of minus theta I. So theta I is the original I is phase. But now the conjugate becomes minus theta I. Make sense? we'll see directly after we keep moving forward. You'll be able to see the results over here. Okay, what's next? Can we write down this? This is multiplication, phasor multiplication, right? So you can do VRMS times IRMS. I have a question. Can we use VM here? You can use whatever number you want to put in there to represent V, right? But since the thing is when we are calculating power, we don't use the magnitude. We use RMS for power calculations. That's why we use RMS. So this V is a RMS V, just to let you guys know. Okay. If a V magnitude is given, you just have to divide it by square root of 2. Okay. And then you got two angles combined. How to combine two angles in the phasor? Multiplication. That's why we use phasors, right? It's because multiplications and divisions are super simple in phasors. Make sense? Can we keep moving with this current status over here? Yes. VRMS times IRMS. What is this? We can convert the angle into the rectangular version of it, and that becomes what? Cosine theta V minus theta I plus J sine theta V minus theta I, right? By definition, from phasor to rectangular. Okay? Refer to the lecture notes and videos if you cannot remember this, but you know, EI or EJ theta equals A angle theta, right? And that equals A cosine theta plus J sine theta. Okay? That's what we have learned. Rectangular form, phasor form, polar form, same stuff. All right, what's next? And this becomes VRMS. Again, no magic to VRMS. It's just basically the magnitude divided by square root of 2 times IRMS. And then what? Cosine theta V minus theta I plus J VRMS IRMS, and then what? Sine theta V minus theta I. All right, got our first conclusion today. Important. You'll see this a lot. And this part, the real part, is called average power. Or sometimes you'll see it's called real power. Denoted as P. And this part is called so the unit is watts. All right. This one is called reactive power. And denoted as Q. And the unit is VAR. Volts ampere reactive. Volts amp reactive. A lot of times you hear about VARs, how many VARs, right? It's this reactive power unit. Okay, now from this conclusion, we draw the following conclusions. You see this cosine theta V minus theta I. Theta V is the phase of the voltage, theta I is the phase of the current, right? So there's the phase difference between the voltage and current. It's usually not good. in the tutorial, the last problem is telling you how to do a phase correction. It's really interesting. For the load, you want the current and voltage in the same phase to have a maximum power delivery or the minimum power consumption to the line. We'll get an example to that on Friday, and so you'll see the differences. So whenever you have a load, eventually you find out the load, the voltage applied to the load and current into the load has a phase shift. And that's bad. So what you want to do is adding another component, either in parallel in series, usually in parallel, to correct that phase, or it's called phase factor here, and eventually make the phase shift to be zero, so current and voltage in the same phase to maximize the power delivery to the load and minimize the power consumption to the line, which is the goal. Okay, that's why we are doing all these calculations. So cosine theta v minus theta I, this parameter is called power factor. You'll see this a lot in the assignments, or PF. Okay, and you'll see P and Q here. It's forming a rectangular complex number for the two different types of powers. Okay, because cosine this angle is giving you P, so that's why here's P. So this is theta v minus theta is a phase difference, right? And Q is here. Eventually, if you do a P squared plus Q squared, and square root of it, you're getting S. So this is S. So S is called apparent power. And this is how you get the apparent power here. P squared plus Q squared equals square root of it equals S. So that's the tutorial covers this, but didn't explain where this comes from. So I derived it for you here, so you can see they come from the complex power. We have so many different names today, right? Complex power is directly just the voltage times the current conjugate. So you have done this a lot in exam 2 and the homework assignments. It's not difficult to find out the voltage and currents in a complex form running through a load, right? Can be a resistor, can be a capacitive load or an inductive load. But eventually, you get the voltage and currents. You will be able to use the voltage and currents to find out the complex power because this is the equation already provided. It's easy to do. So you can easily reach here. If you reach here, you can easily find out the average power or real power on that load or component. Doesn't matter whatever that is, right? Just use the voltage times the current conjugate to find out. Eventually, you'll separate the real part and imaginary power using J. So this becomes the average power. This becomes reactive power. It's asking to calculate these two types of powers. And cosine the V and I's phase difference will give the power factor, which is PF. Okay. So two more conclusions. S is what? S is here is apparent power, which is calculated from the average power and reactive power. So the average power is also called real power because that's a real power consumption. So S apparent power equals what? S times the power factor equals what? S times the power factor equals what? What is the power factor? Here, cosine of this angle. So S times power factor equals what? Average power. Okay. S times sine theta v minus theta I is what? Q. Yeah, reactive power. So you can find out that P is always positive. I mean, calculation-wise, not discussing its absorbing or delivering. But the thing is, cosine, if you draw the angles here, it's either, oh no, I just made a wrong statement. But just within these two quadrants, you can see is either a negative angle or a positive angle, but eventually the P is always positive within this range. But the reactive power can be negative, depending on which is leading, which is lagging, right? Now let's draw another important conclusion here. So if theta V is larger than theta I, what's going to happen? We call it voltage is leading, right? Or let's just use one reference. Keep in mind, I want to use one reference. So current is what? Voltage is leading because voltage is larger. It's like voltage, current. Okay, voltage is leading or current is lagging. If current is lagging, we call we define that the power factor is lagging. And Q is what? Q is larger than 0. And this is definitely an inductive load. Let me see why is that. Is there a way that I can derive it? Anyway. That's the first case when theta V is larger than theta I. Then current is lagging because angle of current is smaller than the angle of voltage. And we call this case a power factor is lagging. So it's basically when current is lagging, power factor is lagging. When current is leading, power factor is leading. That's by definition. Okay? So this has to be an inductive load. As for the other case, when theta V is smaller than theta I, and here's the case, I is bigger and V is smaller. So current is leading and voltage is lagging. So current is leading and we call it the PF, power factor is leading. Q will be smaller than 0 and it's a capacitive load. Why that's the case? Why when current is leading we know it's an inductive load? Can we verify it? Let's try. Let's try, see if we can verify it, okay? So when voltage is leading, what's happening? You got a V, let's say the V's reference angle is 0 degrees. We can do that, right? We can pick up any reference angles. Divided by what? By this? Okay? So this is a positive angle here, right? So eventually this is the current of the inductive load. And this has to be V over whatever the amplitude is, omega L. And the angle becomes minus 90 degrees, right? Who is leading? Can you draw the conclusion? Are you able to follow? Are you able to follow here? What's the amplitude of this guy? This is the impedance of the inductor, right? Impedance of the inductor. And this is basically just this, right? No, this. Here. It's like a 0 plus j omega L, okay? 0 plus, so the real part is 0. Real part is 0. So the amplitude or the magnitude of this rectangular form is just omega L. So you use the magnitude divided by magnitude and phasor minus phasor for the division. And this guy doesn't have a real part, so it has to be 90 degrees. So that's why 0 minus 90 degrees are getting negative 90 degrees. So who is leading for the inductive load? Who is leading? It's very, very obvious, right? Who is leading? What's the angle for the voltage? 0. Can we assume a different angle at the very beginning? Yes, it's just a reference, right? So eventually, if you have a 0 degree for the voltage, what's the phase for the current? It's negative 90 degrees. That's why if you have an inductive load, it's actually giving you this. Voltage is leading the current. So that's why the current is lagging, right? Okay? So that's why we know it has to be inductive load. What about the capacitive load? I is V, let's assume it's 0 degrees, over what? Minus J over omega C, right? What's next? It's V over 1 over omega C, which is amplitude. What about the angle for the phasor calculation? So this is the the magnitude for the phasor, and minus J is giving you what? No, minus J. What's the phasor of minus J? Right? It's minus 1J, right? 0 minus 0 for the real part, 0, and minus 1J. It's negative 90 degrees. So you are getting 0 degrees over what? This. Okay, so eventually you are getting V over 1 over omega C times 90 degrees. So what's the conclusion? Who is leading? Who is leading? Current is leading because current has bigger angles than the voltage. So if current is leading, which is this case, current is leading, we call it power factor is leading, and the reactive power has to be negative because angle of current is bigger than the angle of voltage, so we're getting a negative value here. That's why Q becomes negative. That's why it's confusing. Sometimes you'll see on the tutorial will sometimes give you a solution in the description showing the negative reactive power. It's because of that, right? Because the current is leading. That's why it's giving you the negative reactive power. That's how that works. And then it has to be a capacitive load. That's all the conclusions here. Okay? We'll see you on Friday.